So today we'll be going over maximum, minimums, and saddle points in 3D, three dimensionals. So a saddle point, what that is it's a maximum minimum at the same point. So in this image right here, if we slice it diagonally going left to right this way, we have a minimum point right in the middle. But if we slice it diagonally going from right to left this way, then we have a maximum right here. So that is a saddle point. It also helps that it looks like a saddle point when you look at the graph of the function. You see, put on a horse, looks like a saddle. So then, also another way to look at it is level graphs, level curves. So we know that these four circles, those represent the maximum minimum. That's where it comes to a peak. So like for example, like right here, if this continued, you would have like a peak, as in over here. See these four. But for a saddle point, what you're looking for in the level curve graph will be a hyperbola. So for example, you have one right here. There's a saddle point right here, right in the middle. And also, there's one right here. Let's cut that one. And also possibly one between these two curves. So that's how you can find a saddle point on level curves, and that's how you find a saddle point looking at the graph of it. Okay. The second partial derivative test is a way to find the local maximum, minimums, and saddle points. A saddle point are points where they are both maximum and minimum depending on what slice you take. And the slice I meant was like a slice it this way, you have a minimum. If you slice it that way, you have a maximum. So that's depending on the slice you take, you have a maximum and minimum at the same point. So it's a saddle. So suppose that a function is continuous around a and b, and the gradient of the function is equal to 0. So what we do is take the second derivative of f of x and the second derivative of y of the same function, and then we take the derivative of x, then the derivative of y, and the derivative of y, and the derivative of x, and we take out the determinant of that right here. So then determinants of fxx times fyy minus fxy minus times fyx. And then we take the determinant of that, and that's its value, and the fxx value to determine whether it's a minimum, maximum, or saddle point. And the rules for that are this. Number 1, if DAB is greater than 0 and fxx is also greater than 0, it's a minimum at that point. And if DAB, determinant, is greater than 0 and fxx is less than 0, it's a local maximum. And 3, if DAB is less than 0, f has a local saddle point. And if DAB is equal to 0, then no conclusion can be drawn. And for this to find critical points, you do the same as usual. You take the first derivative of x and the first derivative of y, and set they equal to 0, solve for x and y. So that doesn't change. So we got two examples from the test 2 and the test review. So we have p of xy is equal to 3x to the third plus y squared minus 9x plus 4y. So first we're going to take the first derivative of x and the first derivative of y. For x we will get 9x squared minus 9 is equal to 0. And f of y is equal to 2y plus 4 equals 0. So we're finding our critical points right now. So x is equal to 1, or negative 1, and y is equal to negative 2. So we'll take our second derivative of x and second derivative of y. For fxx is 18x, and fyy it is 2. The derivative of xy and yx are 0, both 0. So our critical points are 1, negative 2, and negative 1, negative 2. Okay, so now we're going to go take the determinants of this. So we plug in fxx to the top left, fyy to the bottom right, and 0 in the top right and bottom left. So 18 times 2 is 36, minus 0 times 0 is 0. So we're left with 36. So let's take a look at our rules. We have a determinant greater than 0. So it could possibly be 1 and 2. But now f(x)(x) is that it's also greater than 0. So then it is a minimum. It's number 1, rule number 1. So we have a minimum at 1, -2. Okay, so now for the point -1, -2, we have, okay, DAB, determinant, again. Oh, and for these points, in the one we plug in for the x, right? So we have 18x, but FYY, we don't have any y's. So we won't plug in x in this case, but you plug in your points to the fxx and fyy, and possibly fxy and yx. In this case, you don't have to fxy and yx. So then you have -18 times 2, which is -36, minus 0 times 0, 0. So look at the rules. We have a determinant of less than 0. It's -36, and all that is left with is number 3. So it's a local saddle point. Local saddle point at the 1 right here. Local saddle point at 1, -2. And that's that for that problem. Okay, so for number 18 over here, we have a function of z. Z is equal to y to the third plus xy squared minus 2xy. So we take the first derivative for x and the first derivative for y. And we get y squared minus 2y is equal to 0. And the fy is 3y squared minus 2xy minus 2x. It's equal to 0. So over here we could factor out y. So we have y times y minus 2. So is equal to 0. So y is equal to 0 or y is equal to 2. So we're going to plug in 0 into fy to solve for x. So we have 0 and over here, and 0 over here. And then we have minus 2x is equal to 0, so x is equal to 0. Then we can plug in 2 over here. So we have 12 over here. We have minus 4x over here. Yeah, minus 4x over here. And minus 2x over here. So we put a 12 to the other side. We combine these two, we get minus 6. So after plugging in 2, we have to 12 over here. We have minus 2x on this side, so we are left with negative 6. So our critical points are 0, 0, and 2, -6. So to find out z value, we plug our points back into a z function. So 0, 0, z is also 0. So we have this one. And at 2, -6, we get 8. So then we have 2, -6, 8. So now we do the determinants. The double x derivative of f is 0 over here. Double prime f of y is 6y plus 2x. And the fxy and fyx is 2y minus 2. These have to be the same. So we take the determinant, so 0 times 6y plus 2x is 0, minus 2y minus 2 squared. We got that, 2y minus 2 times 2y minus 2. So we plug in y. So we have minus 2 times minus 2 is 4, but we have to remember this negative sign in here. So it's -4. So then DAB determinant is less than 0, so then we're only left with number 3, our rule, right here. So it is a saddle point, -4. So at point 2, -6, 8, DAB, we have x, we have the same thing. So then we get the same multiplication, 2y minus 2 squared. So then we plug in -6, and we're going to get -14 squared. So that times this negative over here. So we're going to get -196. And that's also a saddle point at 2, -6, 8. Because its determinant is less than 0. A few things to remember before I leave is that, for example, when these two numbers, the top right and the bottom left, have to be the same. So just here, 0, 0, we have 2y minus 2. That has to be the same. And when you're doing that, remember this negative sign over here, because you're subtracting as in the determinant. And also to remember, lastly, the rules. There's only 3 of them, or 4 of them. The 4th one doesn't really count in my opinion, but they're not that hard to remember. It's determinant is 0, greater than 0, greater than f of x is greater than 0, it's minimum. If it's 1, it's greater than that, but then the other one's less than f of x, then it's maximum. And if the determinant is less than 0, then it's a saddle point. So thank you for watching. It's maximum minimum saddle point, so it's done by Mark and Hamza. Thank you.